Thanks, Mark. Really good intersection of restoration and transportation infrastructure vulnerability and resiliency. And we're going to move on to a presentation by Tom Ballestero. Tom is the former director of the University of New Hampshire Stormwater Center. His general area of expertise is restoration of impaired aquatic systems, and this expertise includes efforts in stream restoration, wetlands restoration, living shorelines, and stormwater management. And Tom has been at the University of New Hampshire since 1983. And the presentation title is The Realities of Green Stormwater Infrastructure and Flood Reductions at the Watershed Scale. So with that, please welcome Tom. You have the.
Thanks, Pete. So without further ado, this was based on long-term studies. We've been doing it in one watershed. Green stormwater infrastructure is entering its third decade now. And so now we can start to ask a lot of these questions that we could only think about back in the 1990s. A lot of this research, these research results were Rachel Hastings, the co-author, her thesis. She's now at Cold Regions Lab with Army Corps of Engineers. So I know a lot of you in here are not stormwater professionals, gurus, modelers. So I'm going to skip through a lot of the fodder that I put in here. I believe the presentation will be online for those who want to see the details. But I think the important things are kind of the results. Many people going back decades have been looking at green stormwater infrastructure as the panacea, the solution for all of our stormwater problems. And it does solve a lot of them, but it doesn't do everything. There's no silver bullet. And I know 20 years ago, American Society of Civil Engineers was asking me questions or wanted me to write an article about how green stormwater infrastructure was going to stop all of the flooding in the United States. And I kind of had to ask them to put the brakes on that because, again, it's got a niche. So very simple questions we were posing. And part of this was a comparative question because now at the watershed scale, we had some of these answers. And one is, given the 800-pound gorilla or the elephant in the room, which one's worse, climate change or impervious surfaces? And it's actually a pretty interesting question because impervious surfaces, we can actually resolve issues associated with them relatively short timescales. 1 to 5 years, we can start implementing things. Climate change is occurring over very long timescales, and it's going to take global types of things to arrest climate change, although we can react to it as far as resiliency, sustainability, and retreat. So that was one of the questions, you know, which one's kind of worse? And then the other one is, when we look at green stormwater infrastructure, how does it actually address flooding in urban settings? So I think most of us are in tune with all of the predictions of climate change. I think we're starting to see some of those play out. I think the scariest thing that I tell my students about climate change is not that we see these trends. Sea level rises is increasing. Extreme floods are getting worse. Droughts are getting worse. That's kind of a trend in the mean. And as most of you familiar with probability, there's other statistics, standard deviation, skewness, et cetera. And there's also variability and trends in those other statistics, which actually drive the extremes more than just a trend in the mean. So what you're looking at are some of the predictions of what would happen with extreme precipitation. And as you can see, we in the Northeast are getting some of the most dramatic changes in extreme precipitation. And what that does is when you look at a probability plot here, the blue is the 1-year storm and the 24-year storm for different return periods, a 100-year event, the 50-year event, the 20-year event. And when we see this change in the probability, we're seeing these probability distributions shift to the left, meaning that for the same type of return period, 50 year, now we get a larger depth. Okay, that's what we're seeing. So we're seeing these changes in the probability distribution. And this is a probability distribution, but it's just the tail of the distribution. It's not a simple bell curve like you're used to seeing. In the state of New Hampshire, we address climate change in a very simple way. We say to design for climate change and projects they're going to be in existence, hopefully in the next 50 to 100 years, we increase the design rainfall by 15%. So it's a very simple way of addressing it. Those of you who are familiar with green stormwater infrastructure, it's typically statically designed, and I'll explain what that means. And we typically use a 1-inch depth of rainfall, and then we deal with the runoff from that rainfall. In the state of Maine, chapter 500, you look at the 1-inch depth of rainfall on all impervious surfaces, and then 4/10 of an inch on all other landscape areas. And so you take that runoff, which can be from a hydrograph, but you calculate the volume and then you plop that into the green stormwater infrastructure system. That's a static design. Water goes in instantaneously, which is interesting because 50 years ago in the 1960s, 1970s, how we did stormwater infrastructure was dynamically. The water came in and the water came out at the same time. But you know, in the adoption of green stormwater infrastructure, I think it's easier for people to design things statically. And then ultimately now we're moving into dynamic design, which actually is giving you smaller systems and it's saving us money. So for the Berry Brook Watershed, this is in the town of Dover, New Hampshire, close to the Maine border. It's a 200-acre watershed. The most important thing is when we started this project back in the early 2000s, this watershed has 30% impervious surfaces. That 30% is still there. We didn't remove it. But the difference is that all of that impervious area was unmanaged as far as stormwater controls. As you manage more and more of it, you reduce the effective impervious cover. So we brought that down from 30% effective impervious cover down to 10%. We didn't remove asphalt. We just managed the stormwater. And why 10%? Those of you who are familiar with the literature, when watersheds start from 0% impervious cover and increase somewhere between 5 to 10% impervious cover in a watershed, you start to see statistic differences in water quality in the receiving waters, as well as the biota. So 5 to 10% is kind of a magic number for stormwater. So one of the things we did in this watershed over a 7-year period was we reduced the effective impervious cover. We daylighted over 1,000 feet of stream. A lot of that was converted into wetlands at the headwaters. The headwaters of this watershed is a Hannaford shopping center parking lot. So it from the get-go, it's got challenges. Oops. So I won't go over all the systems, but a lot of the systems we put in there are very typical systems, again, statically designed, and we've put in over 24 systems now. So what we had was a system or a watershed that we started with no green stormwater infrastructure, 30% effective impervious cover, and we were taking data of the rainfall and the runoff. We did all the implementation and we measured the rainfall and the runoff. So now we have information to calibrate models. Without going into all of this, we used PC SWIM, which is a proprietary version of the EPA SWIM model. It's got a nice calibration tool because even as what Kirk was talking about with his models, there's a lot of bells and knobs and whistles that you can play with. And what you're trying to do when you have calibration data is get the set of information that gives you the minimum error with all of your observations. And so we had a lot of data sources where we could input everything because again, we're modeling watershed hydrology. The biggest criticism I have of the SWIM model is it's not coupled with groundwater. So although we could demonstrate we were infiltrating a lot of water into the ground, it doesn't show up in the stream in SWIM. So I can't really show you good volume balance information, but you'll see it on some of the calibration hydrographs. When we're modeling the watershed, we obviously disaggregated into smaller subwatersheds. And one of the thought exercises we did was to take this watershed with 30% impervious cover and numerically reduce it down to 15% and 0%. And so in SWIM, each watershed has a certain percentage of impervious cover. And all we did was reduce that from the 30% to 15% to 20%. And the watersheds look a little different with and without the green stormwater infrastructure, because part and parcel to our implementation, we kind of modified some of the watershed boundaries. So we did have calibration data. Some other graduate students were measuring the stream flow at different locations. We had a rain gauge on site, but on campus, we had rain gauges that took data and reported it and recorded it every minute. So that's the data set we used. We basically looked at two different types of simulations. One was a 10-year continuous simulation, which is one of the nicer things you can do with SWIM. And the other was the common or traditional event-based model, the 100-year precipitation or the 50-year precipitation. They're two very different types of questions you ask. The design events you may never see when you're trying to monitor a project for 10 years. And we didn't see a 50-year flood or a 100-year flood in the 10 years. So some of the calibration hydrographs, they never look pretty, but again, what you'll see is this is pre-implementation with 30%. So this was the original watershed before we started to play around with it. And after the green stormwater infrastructure implementation post 10 is what that means. And so the green is what the model would spit out. And again, what you see is the model can't pick up the groundwater flows afterwards, but we do a decent job. And we didn't do just one storm. We looked at a number of storms, a few dozen storms to do our calibrations. So once we had a calibrated model, again, we could look at a long-term hydrograph, and these are just the precipitation records from the Morse Hall gauge. And we could start to look at some of the variables of interest to us. And again, the title of this talk was to look at flood peaks, and that's what I'll focus on. But we looked at some of these other things, the amount of water we reduced, the runoff, and the infiltration. So again, in New Hampshire, we could look at the extreme precipitation for today, and that extreme precipitation for today is up here. I show the 1 hour storm as well as the 24-hour storm. This is the duration of precipitation. Why 1 hour? Well, the time of concentration of this watershed with 30% in impervious cover was about 26 minutes. So a 24-hour storm isn't really the design storm. What you really want to do is match the storm duration to the time of concentration. But I'll focus on the 24-hour storm because that's typically what we typically would use in design. And again, for climate change, if you look at just the 2-year 1 hour, that's about 1 inch, 15% increase. So these are just increased by 15% over those. And that's what we use for the design events compared to the long-term simulations. So again, two different types of simulations to get two different types of variables. And then these are the type of case studies that we looked at. Those in blue were the ones we calibrated. So once we had a calibrated model with 30% impervious cover, we could reduce the impervious cover to 15%, reduce it to 0. Why? To answer that simple question I posed earlier, which is worse, the 800-pound gorilla or the elephant? Climate change or impervious cover as far as hydrologic consequences? And then we could also look at how climate change would be addressed by the green infrastructure itself. Just looking at some of the results now. What you would expect as you remove impervious cover is it takes the water longer and longer to run off. At the same time, that reduces flood peaks, of course. If you just took this watershed with 30% impervious cover and did the implementation we didn't really get as far as we would like to have. And the reason for that is when you get these large storms, green stormwater infrastructure, again, is designed for a 1-inch storm. So storms that get much larger than that just go into bypass mode. So you can only do so much. when we looked at that 10-year record, we could look at the largest flow, the peak flow of each year. So these are the peak flows each year. And then we could look at the peak flows after we put in the green stormwater infrastructure. And you can see we get significant decreases. Interestingly, here's a storm with a peak flow of 26 CFS, the largest peak flow that year. And we only reduced it about 1 or a little more than 1 CFS. Here's another one with 25. We reduced it significantly more, 25, reduced it significantly more. This is because of how the rain fell from the sky. You know, if you have a thunderstorm, you'll see much less of a change than if you had a long duration, low intensity storm. That's where green infrastructure works best. So, you know, you're starting to see the realities that an event-based storm would never give you. So this is the take-home message. If you had to pay attention to anything in this talk, this is the slide. So this is the watershed before we did anything. This is the watershed after we implemented green stormwater infrastructure. This is a one-to-one line, and what we're plotting is the peak flow, peak discharge. So if we had no effect, everything should fit on this line. And what you see clearly is for small storms, and these are storms typically less than the 2-year event, which would be less than 3 inches on a 24-hour basis. Green infrastructure is dramatically reducing peak flow because it's designed around that type of storm path. Out here, and as you'll see in future slides, the 2-year peak discharge is around 25 CFS. For the 2-year and larger, there's very little impact of the green stormwater infrastructure on these high magnitude storms. Because again, if you have in this area of New Hampshire, the 100-year rainfall is 8 to 9 inches. If you're designing systems on 1 inch and they're all going into bypass mode after that, you're not going to have that much of an impact on these big storms. So again, the biggest impact of green stormwater infrastructure are the very, very common events. This is the big take-home message. Again, we can demonstrate, obviously, we put a lot of more water into the ground. That's the intent of green stormwater infrastructure. For the extreme precipitation events, again, we can look at the 2-year event. We'll see a big reduction in the flood peak. For the 100-year event, you're not going to see that much of a reduction in the flood peak. And so, again, busy table. If we look at the different return periods and just focus on the 24-hour event, you can see that as we go to larger and larger return periods, you get less and less of a reduction of the peak event. That's what you'd expect. So kind of as a summary, you know, when we look at extreme precipitation, we can get some peak flow reduction, but you know, if you're really after peak flow reduction of those events, that's a different design. Green stormwater infrastructure is only putting a dent in it. In the long term, you can show that you have dramatic consequences in the blue collar types of events, everything that normally happens. That's where this 1-inch design depth came from for green stormwater infrastructure. On most of the East Coast, not about 90% of the events, daily rainfall events, are 1 inch or less. So I think I will leave it at that because I think I'm getting close to the end. And oh, I have 2 minutes less, then I'm going to go back. So the one question I didn't specifically address, and this kind of had some, I don't know what happened to this slide, but the simple question is when you look at impervious cover versus climate change consequences on watersheds, impervious cover by far and away is going to be generating the most dramatic impacts on your watersheds. So if anything, you know, that's our primary focus right now. If there's no stormwater management in your watersheds, you need to address green stormwater infrastructure now. Climate change will happen, and you can certainly include that, but it's the impervious cover, and this is just hydrology. Water quality is the other thing that GSI is doing big improvement on. And you can almost tailor green stormwater infrastructure to almost any contaminant of interest to you, whether it's sediment, nutrients, microbial. Probably not going to do anything about PFAS, but someday they may have something for that. So anyway, I'll leave it there and we'll go on to questions. Thank you.